Okay, so exam 2 is on Wednesday. And the topics are everything up through particle kinetics. And just thinking about the big picture, this is particle kinetics in a non-rotating coordinate system. So we'll later talk about how you would treat particle kinetics if you don't have an inertial coordinate system. All right, anybody have any homework questions?
Number 12,
Number 12. Nope. Okay. So number 12. Yep. So that's the one where you have a Ferris wheel. Wow, these are big books if this radius is 6 meters. The radius of this Ferris wheel is 6 meters, and you have some books down at the bottom. And we're using a funky coordinate system. So the x-axis is to the left and the z-axis is up. What does that mean about the y-axis? It has to be one way or the other. So x cross y is equal to z. Y cross z is equal to x. But y always has to be the weird one. So x cross z is equal to negative y. And so the y-axis has to be coming out of the page. And that's going to be important for figuring out the direction of the angular velocity and angular acceleration. The angular speed is 2.5 radians per second. It says, I guess, that it's going this way. So this is 2.5 radians per second. And it's speeding up at 8.5 radians per second squared. That means the angular acceleration is in the same direction as the angular velocity. And we want to calculate the force vector. The middle book applies to the top book. We're going to assume that there's friction between these books. Otherwise, they would just slide off of each other. So the force vector, the middle book applies to the top book. That means when we do our free body diagram, we can just isolate the top book and we'll be able to calculate that. And the idea is that the weight, is down toward the bottom of the page. That's the orientation of a Ferris wheel. Okay, so let's figure out, we're going to go to Newton's second law. But there's a lot we can figure out about the acceleration. So let's figure that out first. All right, well, the acceleration of an object in circular motion this is the watermelon equation. So all ripe watermelons will rot. And now we just have to figure out alpha, omega, and r. The r vector is in the negative z direction, and the radius is 6 meters, so r is 0, 0, negative 6. the angular velocity and angular acceleration. Now, in order to do this, we had to figure out the direction of the y-axis. So we figured out that the y-axis is going this way, the rotations are this way, so both of those are in the positive y direction. So omega is 2.50 radians per second, and alpha is 8.50 radians per second squared. So the acceleration is 8.50 crossed with 0, 0, -6 plus 2.50 crossed with the quantity 2.50 crossed with 0, 0, -6. This one is in the x direction, 1500. And we're crossing that with 2.50. Cross this one, and you get 51 in the negative x direction. Which one? Yep, you're right. Thank you. And so we get the acceleration is -5100 crossed with 0. Oh no, not crossed with. I'm sorry. We're just adding these. So this term is in the z direction, 37.5 positive. So the acceleration of that top book that we're looking at is -51, 0, 37.5. Yeah, if this problem had given heights of the books, thicknesses of the books, we'd have to take that into account, and we'd have to think about which of these books we were actually isolating. Since we're sort of picturing that everything's on a big scale and these books are pretty relatively thin, we're sort of treating them like they all have the same acceleration. But that is something you would have to consider. All right, so we have that acceleration. Now, free body diagram of the top book. They each weigh 1 kilogram, I think. Yes. So there's a weight force down of 1 times 9.81, so 9.81 newtons. And then there's a normal force and a friction force. I'm just going to treat that as two unknown things. We don't know anything about the coefficient of friction, so we can't do anything more than just try to calculate both of these components. This is the force vector acting on the top book by the middle book.
That's a little confusing.
Mm-hmm.
That includes normal force.
Yeah. I mean, the way, so you could break it up into, if you'd rather write that as a normal force and a friction force, you can do that. What you would see is, like, the benefit of writing it as a normal force and a friction force usually is that you can write the friction force as a function of that normal force, you know, as the coefficient times the normal. That's what you did in physics 1. But we don't know the coefficient, so we can't do that, you know. So we just have this vector that has a normal force that way, friction force either that way or that way. The sign will work out on its own. But the nice thing about this representation is even if your coordinate system wasn't lined up with the incline, you can still write it this way, you know, whereas to write it as a normal force and a friction force, you'd have to do all the trig to figure out the orientations of those unit vectors. All right, so now Newton's second law for the top book. I'm going to write it in 3D. All of these forces are in 2D. And you could just do it as 2D with your components being X and Z, but we're not so used to doing that. So I'm gonna write this as so the weight force is in the negative Z direction. So we have 0, 0, negative 9.81. Plus FTM X 0 FTMZ. And that's all the forces. And those are equal to the mass of what we're isolating times the acceleration that we calculated, negative 51, 0, positive 37.5. And so FTMX is negative 51 newtons. And FTMZ is 37.5 minus 9.81, so that's 27.69. Oh yeah, added. So 47.31, something like that.
So you just moved gravity over.
Yeah, I mean, this is just two different equations. So the first one says 0 plus FTMX is equal to negative 51. You know, 1 times negative 51. And the second equation says negative 9.81 plus FTMZ is equal to 1 times 37.5. Any other questions about that one? Okay, so what do we get? We get that, so this thing is, the Ferris wheel is moving this way and speeding up, and we got that the X component of force is in the negative X direction. So in order for this to stay in that circular motion as it's speeding up, the friction force from the middle has to push on it that way, the negative X direction in this case. What we're used to as being the positive X direction. But that makes sense intuitively. And then the Z force is positive because that middle torque is pushing up. Yep.
Would there be any friction force the acceleration, the speed was constant?
You're right that there would not need to be any friction force. Yep. acceleration would have no tangential component. All the acceleration would be centripetal. Yep. Yes.
So whenever you know your examples, you write the R in front of the second law with the R.
R.
So like all the examples. Once you write R into law.
Oh, rotational. So if I'm doing the moment equation, so when we get to rigid bodies, we've already in D form gotten to rigid bodies, so that's why you've seen it in D form. We haven't yet. That's sort of the next thing we're going to get into. But then there are two equations of motion when you get into rigid bodies. There's Newton's second law, and then there's sum of the moments is equal to I alpha. And since that has the same form as Newton's second law, I think of that as like the rotational version of Newton's second law. So that's what it means, Rn2L, rotational Newton's second law. That's an exclusive to this class. You won't see that anywhere else. So it's always nice to get notation you're not going to ever see again. Any other questions about this one? Any other homework questions? Okay. 15. Oh God, that one looks impossible. No. Okay. So that one, there's an object moving. Okay, so the way it's drawn, it sort of looks like a disc or something, but all we're tracking is the motion of this object as it's in circular motion around the center of this thing. And this, if we call this the point C and we call this the object, that point C is moving along a path like this. And it's moving in the positive x direction along that path. And we're given that the mass of the object is 0.01 kilograms. It's in uniform circular motion with an angular velocity. Well, it says that it's rotating clockwise, so the angular velocity is negative 15 radians per second.
That uniform circular motion means that this body or C will also have some angular acceleration.
No, the angular velocity is just referring to that O around C. And uniform means that there's no angular acceleration. And the circle's radius is 0.25 meters. What's the net force on this object O? And I didn't write down the velocity, but the velocity of C given as a function of x is 3 for the x component, 2x for the y component. Okay, so we have some information about the center of the circular motion, how it moves along this path. Although it's not given as a function of time, so we're not going to just be able to take the time derivative. And then we have information about how O is moving around C. Okay, and I don't know. Notice that this is like a pretty complicated looking problem. Like what it's asking you to do is pretty complicated, but we're just going to break it down into 3 sort of simple techniques that we've done a bunch of times. We're going to do a relative motion, to represent the acceleration of O, given that we know how O moves around C and we know how C moves. We're going to use the chain rule to get the acceleration of the point C. Okay, and we're going to use circular motion to calculate the acceleration of O around C. All right, well, so the big idea is that the acceleration of O relative to the ground is equal to the acceleration of O relative to the center plus the acceleration of the center relative to the ground. And this is going to be circular motion. And this, we're going to have to use that chain rule approach.
But we have a velocity vector already.
We have a velocity vector, but to come up with, yeah, that's right. So what we're not going to have to do is that thing where you find a unit vector tangent to the path, which always makes the derivatives super messy. So that's good. The chain rule will be nice and simple for this. Okay, so acceleration of O relative to C. That's just circular motion. So that's alpha cross R plus omega cross quantity omega cross R. There's no alpha because it's uniform circular motion. This problem didn't require a certain coordinate system, so I'm just going to use the usual one. The z-axis is coming out. So if this omega is, if this circular motion is clockwise, that's in the negative z direction. So our omega vector is 0, 0, negative 15. And our r vector is in the negative x direction with a magnitude of 0.25. So negative 0.2500. That's in meters. And so the acceleration of O relative to C is equal to 0, 0, negative 15, crossed with the quantity 0, 0, negative 15, cross negative 0.2500. Well, that is 3.75 positive in the y direction. And then we're crossing that with 0, 0, negative 15. And so the acceleration of O relative to C is in the positive x direction, and it's 56.25. Positive 56.2500. Does it make sense that it's in that direction? So remember, what we're doing here is just the circular motion, assuming that C was fixed. We'll deal with the fact that it's not fixed next. But if this is a uniform circular motion, no angular acceleration, does it make sense that the acceleration of O is in the positive x direction? Yeah, because it's all centripetal acceleration. Okay, and now we'll go to the second part, the acceleration of c relative to the ground. Well, we know that the velocity of c as a function of x is 3, 2x. And so the acceleration of c as a function of x, the definition is dv dt, but we don't have it expressed as a function of t. So we'll use the chain rule, and this is dv dx times dx dt. So dv dx is 0 in the x direction, 2 in the y direction. And then we're multiplying it by the x component of the velocity, which is 3. And so we just get an acceleration of 0, 6. And so now we can go back to relative motion. The acceleration of O relative to the ground is equal to the acceleration of O relative to C plus the acceleration of C relative to the ground, which is 56.25. This is in the plane. So there's no Z component here. So this is just 56.256, 0 for Z, meters per second squared. And then what it asks for is the net force on it. That's the acceleration. Newton's second law says that the net force is the mass times the acceleration. We had a mass of 0.01 kilograms. So multiply that times the acceleration, and you get 0.56250 newtons. What? Should it? One. That's right. If, oh, yeah. I'm sorry. So 0.06. Okay. So this should be 6. This should be 0.06. Yeah. Any questions about that one? I mean, think of it like, I don't know. You guys there's a test on Wednesday, so maybe you're feeling grumpy and you don't want to do this kind of stuff. But that's a pretty complicated, conceptually, that's a pretty complicated problem with a lot of stuff going on. And, we have these simple tools that you can build on top of each other to come up with solutions for pretty complicated things now. You might have seen these topics in Physics 1, but my guess is that you wouldn't have known how to approach a problem like this. So good job.
So it kind of looks like all of kinematics.
Yes, all of kinematics is in kinetics. That's correct. Any other homework questions? Okay, so a 20-kilogram child rides on a carousel. This is still kinetics, yeah. Yeah. The simpler one has the longer name, and the complicated one has the shorter name. Like it's backwards. Okay, the child has a mass of 20 kilograms. The carousel has a radius of 2.2 meters. And spins with a constant angular velocity of 5 radians per second. It doesn't say which direction. What's the contact force applied to the child by the carousel? What's the normal component? Magnitude of the friction, minimum coefficient so the child doesn't slip. Okay, so let's choose a coordinate system that's like x this way, y this way. So the child, the way I have it drawn, is sitting right in at negative 2.2y, and then z up. The first thing we have to do is figure out the acceleration of the child. So the acceleration is alpha cross r plus omega cross quantity omega cross r. Notice that the way you group cross product is important. You know, matrix multiplication you can group in any way, but if we try doing omega cross omega before and then doing r, what's a vector cross with itself? 0. So that order is important for how this works. That goes away. Our omega vector, the way I have it drawn, and you could draw it a different way and it would all come out different. The answer to the questions, if you do it right, would all be the same. But the way I have it drawn, this is in the positive z direction according to the right-hand rule. So omega is 0, 0, 5. The r vector is 0, negative 2.20 in meters. And so the acceleration is 0, 0, 5 crossed with the quantity 0, 0, 5 cross 0, negative 2.20. So you cross these two, you get something in the positive x direction. That is 11. And then we're crossing that with 0, 0, 5. And so the acceleration of the child is 0, positive 55, 0 meters per second squared. All right, so now we have to do a free body diagram because we're going to use Newton's second law. So a free body diagram of the child. what loads are acting. There's a weight force that's 20 times 9.81, so 196.2. And then there's a contact force, which is made up of the normal and the friction force. So I'm going to write it as a normal force that's in the positive z direction, and a friction force that's in the positive x direction. Well, actually, okay, be careful here, because this is a three-dimensional problem. And so I'm going to break this up into, so we don't know the direction of the friction force. In 2D, you know the direction of the friction force, or you can pin it down to at least a plus or a minus. But if you're doing a three-dimensional problem, the friction can act anywhere in the plane of the surface. So I'm going to say we have a friction force in the positive x direction that could end up being negative. I'll call that Fx. And then a friction force in the, so if I keep drawing this sort of the way I did before, that's going to be like this direction. And that is the y component of the friction force. Okay. And so Newton's second law if you're really thinking carefully about this, you could notice that there's not going to be any x component of friction because, well, there's a couple of reasons that it would work out that way, but the simplest reason is that there's no x component of acceleration, so that's going to come out being 0, but this will work out fine. So we're just going to say, okay, there's friction, it acts somewhere in that plane, so we'll give it 2 components and write out Newton's second law. So we have 0, 0, negative 196.2 for the weight force. The normal force, 0, 0, n. The friction force, Fx, Fy, 0. And all that's equal to the mass times the acceleration, which is 0, 55, 0. So the first equation says Fx is equal to 0. The second equation says Fy is equal to 1100. And the third equation says the normal force is equal to 196.2. Things are looking really bad for this kid. This kid is not staying on there. So these are the forces that would have to be applied for this kid to remain in circular motion. If those force requirements are not met, then this kid is not going to stay in circular motion. In this case, this is an unrealistic requirement for friction, and so this kid would start to slide and go off and demonstrate why they don't put these in playgrounds anymore. Okay, so we got these forces. So now the next question is, what's the coefficient of friction? Is that the next one? What's the normal component? Okay, well, we already separated it up into normal and friction. What's the magnitude of the friction force that we found? The magnitude is 1100 because there's no x component. And so then the last question is, what's the minimum coefficient of static friction required so the child doesn't slip? Well, the friction force, and that's the magnitude of the friction force, is equal to the coefficient of static friction. Well, this is static friction, so you can think of it as the friction force can only get as big as the coefficient times the normal. Okay. And so if the maximum friction force is 1100, what we have is that 1100 is equal to the coefficient of static friction times 196.2. And so you get a coefficient of static friction that's over 5. Can someone divide that out exactly? 5.6 or something. 5.607, and that's a pure number, the coefficient of friction. Okay, well, there's no pair of materials on Earth with that coefficient of friction between them, so yeah, he'd have to be fixed in some way, yeah. You know, that's too high. So this kid would slide off unless they're holding on to something or glued or whatever. Coefficients of friction can get bigger than 1. Like rubber and cement have a coefficient of friction for certain kinds of rubber that I think get up even higher than 2, but I've never seen a number as big as 5. Most of the time it's between 0 and 1. One thing that says, by the way, that's sort of interesting about, so a material that has a coefficient of friction higher than 1, if you're capable of producing some given force, 1,000 newtons, and you want to hold, say, a tire and a piece and concrete together, you get more benefit applying that 1,000 newtons that you can apply down towards the surface than you do applying it sideways to hold the tire in place. That's what a coefficient greater than 1 means. You get more force by applying, you get more restrictive force by applying a perpendicular force than you do by applying the actual restrictive force. That's kind of cool. Any other homework questions? Okay, so Wednesday's the test, and then Friday we'll get on to new material, which we're going to start doing rigid bodies, where we can start to deal with the orientations of things and calculate contact forces, break up contact forces into separate parts. You have a hinge over here, you have a whatever over here. And eventually that'll lead us into being able to do calculations with linkages, where you have a whole bunch of members connected by, say, hinges, pin joints, and you can calculate if you apply a force to this one, what happens to the end of this one. That's sort of interesting stuff. Okay, that's all.